Okay, let's start. I hope everyone can hear me. Good morning. So this is our first real meeting regarding physics. And today we're going to try to cover the good part of chapter 21. And there are some problems assigned from this. I already solved them and made video recordings of them. I will make them available on YouTube. I'll post links on OptiClass. But if you have further questions, I will be happy to try to solve these in class as well. Now, before we begin, I'll ask you to turn your cameras on if possible. Obviously, there could be reasons why you can't do this, but I'd appreciate to see some faces. And secondly, I will be speaking mostly in English, but if you have a question and for some reason you cannot ask this in English, you can ask it in Turkish. I'll try to translate both the question and try to answer in a mixed language so that you can follow this. Right? It's much better to ask questions than in Turkish than not to ask questions at all. Right? Try to ask it in English, but if it doesn't work, I prefer that you ask some questions rather than avoiding asking questions because of a language problem. Right? This is not an English class, this is a physics class. Okay, so this whole semester is about the electric and magnetic phenomena. And this involves the electromagnetic force. It turns out that this was noticed quite early. The electromagnetic force was noticed quite early in the antiquity. And in fact, except for the fact that you're not floating in space, that you're not leaving the surface of Earth, everything you see around you is because of electromagnetic force. Right? So there are four fundamental forces in nature. There's the electromagnetic force, there's gravity, there's strong force and weak force. The last two are nuclear forces. They are very short range, so they have only an indirect effect on our everyday life. Gravity is, what keeps us on the surface of Earth, but it's very weak, as we are going to see in a moment. And electromagnetic force is responsible for everything. Okay? Not only, this information is coming to you by electronic means, literally, but like the fact that I can speak, my body functions, all of that. My atoms that form my body are formed together. The molecules have certain properties. All of that is electromagnetic force. Yeah. But as I said, this was noticed very early in antiquity, and it's, I think, one of the few experiments that every high school in Turkey does. Right? So you take a comb, you rub it on your hair, and then using this comb, you can pick up little paper pieces. Right? So something similar was noticed in antiquity, that they took a piece of amber, you rub it on wool, and then you can pick up some dry leaves. Right? In fact, the name electron comes from the Greek word for amber. Now, what's going on here? Right? First of all, this is, because you are familiar with this, it might not look something strange, but there's something very strange here. Right? When you're picking up those little paper pieces, you're overcoming the gravity of whole Earth. Right? All of Earth is attracting those down, and you're picking them up by using a simple comb. So this is why we say gravity is weak and electrostatic force is very strong. Now, obviously, this has some range. It's not picking up everything around it. It's not picking up all the pieces of paper all over the world. They're still being pulled down by the Earth itself. So it has some limited range. And we'll come to that, why it has some limited range. But it is very, very strong. Right? For the limited range, it can actually overcome the gravity of whole Earth. And you are also probably familiar with the magnetic phenomena. Like you can take a magnet and put it on your fridge. It's just going to stick there. And again, it's going to overcome gravity. Right? It just sticks there. It holds onto the fridge, despite the fact that all of Earth is pulling this little piece of magnet down. It turns out that this electric and magnetic force are the two sides of the same coin, that they're not that much different from each other. But we're not going to really go into details of this. Now, how can we understand this? How does this work? Now, it turns out this is something related to what we call charge. And so when you rub an object on another object, what you're doing is you're either depositing charge on the object or you're picking up charge from the object. And so charge is an empirical observation. So it's something that we observe. It's not obvious that it should be there, that something like this should exist, but it is there. Empirically, we know that charge exists. And when we rub objects, they remove charge or deposit charge to the object. Right? So it turns out that what's happening here in reality is that you're either removing electrons or putting electrons on the object, and electrons are charged objects. Right? Now, because of this, because we become charged by removing charge from a point or by putting charge onto a point, the total charge is conserved. Okay, so rubbing does not create charge. it just redistributes it. Some object is going to have some excess charge, and some object is going to have a depletion of charge. Right? So of course, you could put this the other way, and it's going to be more appropriate. What happens is that because charge is conserved, you can't create or destroy it, but you can have an imbalance in an object. Okay? So this is like money, though you can actually create money, right? But your bank deposit could be zero, it could be negative because you have some credit card balance, or it could be positive because you put in some money into your account, and so on and so forth. Okay? Assuming that you can't create money, despite the fact that you can, then the situation is going to be similar, right? But you don't need to think in terms of money, especially because money, can be converted into other things. Charge cannot really be converted into other things. Right? Now let's just start writing this down. And for this lecture, I'm actually going to be using my whiteboard. So hopefully this is going to work. Well, yeah. Just this, hey, yeah. I already tested this to some extent, and hopefully you'll be able to keep hearing me. Now, one thing I have said is that the charge is conserved. This is an important property. Can you read this? Is this large enough? Well, this is a hard question to answer.
Yes.
Is there anyone who cannot read this actually? All right. I'll assume that people who can't read this actually have functioning microphones, and because nobody spoke, everybody can actually read. But if you can't read this, just let me know. Another thing that I don't know if I mentioned this in the first lecture, but one of the most common complaints about my lecturing is that I speak fast. Okay? And this is not just from my students. And my mother complains that I speak fast. When I'm speaking Turkish, she can't understand what I'm saying. So I try to slow down. I try to speak clearly, but it's who I am. Right? So you'll need to stop me. I know it's not totally fair to put the burden of this on you, but I have nothing else to do. Okay? So you have to just stop. Say, oh, I didn't catch that. Could you repeat that? Can you slow down? Something like this. Right? I don't mind repeating myself. There is no point in going fast and not learning anything. If we go slow and we learn something, it's much better than not going fast. Yeah? Anyway, so the charge is conserved. Another second property, that the charge comes in two flavors. Right? Again, there's no fundamental reason for this, but it's just the way nature is. You can have two kinds of charge, and these two different kinds of charge attract each other, and the same kinds of charge repel each other. So let's write this down as well. Like charges repel, and unlike charges attract. Now, as I said, there is no reason why this should be the case. There could be three kinds of charges. In fact, in quantum chromodynamics, we have three kinds of charge. Okay? And then there's some more complicated mathematics involving that. But for electrostatics, for electricity and magnetism, there are just two kinds. Okay? So we call these positive and negative, just arbitrarily. Okay? It turns out that when you rub objects between each other, they charge the same way consistently. So if I'm rubbing amber on the wool, the amber is going to get charged always the same way, and the wool is going to get charged with the opposite way. Right? So you can do more complicated, more accurate experiments. You don't need to take a piece of amber and take a piece of wool. There are some experiments that are recommended by the Scotch tape. So just look for this. Scotch tape experiments. And I have a large number of Scotch tapes. If you can't afford to get one, just stop by my office. I'm happy to lend you one. And you can make experiments with this and get more accurate observations. But as I said, so you can have similarly charged objects, or the same kind of charge on objects by using similar materials and using a similar procedure to charge them. And then they're going to be charged the same way, and they're going to repel each other. And the unlike charges, that when you deplete charge from an object, you're going to charge this object in a particular way, the other object is going to be charged the opposite way. They're going to attract each other. Now, this, of course, brings up the question, what about the, what about piece of paper? Right, so we talked about that you can pick up this piece of paper, and it turns out that you can pick up those pieces of paper regardless of what kind of object you're charging. As long as you're charging an object, it's going to pick up pieces of paper, right? And the objects, the piece of paper are not charged. I do not charge them. I just tore the paper apart and got these pieces. So what's going on here? So it turns out that this is actually complicated, and this is related to the so-called polarization. Okay? When we bring the charged object close to the piece of paper, they become polarized because of their nature. They're organic, they have wood, so the electrons are not evenly distributed, and so on and so forth. But to understand this, we need to go into the atomic structure of the matter. And I'm going to go into this very briefly. And this is one of the most important discoveries of modern physics. I'm calling this atomic hypothesis because that is what it was called originally, but it's no longer a hypothesis, obviously, right? It's atomic theory. We now know that the atoms do exist, they have a certain structure, and so on and so forth. Now, what is this theory? What does this involve? Well, every atom is going to have some nucleus that by arbitrarily we call positively charged, and there's going to be some electrons going around it that are going to be negatively charged. And this is my nucleus, and this is my electron. The atomic hypothesis says that every piece of matter that you see around you is formed of atoms, and these atoms have a certain structure, and all the properties of the matter that you observe comes from the interaction between these atoms and their intrinsic properties. Okay? So this is something extremely important, right? So the physicist Chap21 said that if like the whole civilization was going to be destroyed, and you could pass just one piece of information, something that you can say in a couple of sentences, he will pass this information to the next generation. Okay? On this, you can build a lot of things. And it wasn't easy to discover this. This was one of the breakthroughs of the 20th century physics, or end of 19th century physics, let's say. Okay? So to understand what's happening to a piece of paper, we have to understand how the atom works. So what happens is that when you have multiple atoms, let's say that I have something like this. So this is a model of the water molecule. We have an oxygen atom here and two hydrogen atoms here. The electrons are going to be just going around these nuclei. Okay? And they're not going to spend equal amount of time on these, but they're going to spend more time on the oxygen, which is going to be equally charged, than the hydrogen, which is going to be positively charged. And because of this, and because we're going to see that this electric attraction depends on the distance, if this molecule can rotate around, it can orient itself such that the attracted part is closer to the attractor, and the repelled part is farther from the repeller. And because of this, the attraction force wins over the repulsion force, and it's going to be attracted. Right? So this is what's happening with the piece of paper. Okay? But this is something very complicated. I don't want to go into the details of this. Just know that this is not something you can easily understand by saying that there are two kinds of charges, and unlike charges attract and like charges repel. Right? So are there any questions? I'm probably going a bit fast. I'm assuming you know part of this. I'm assuming that you have seen this in high school and at least took a look at the book and talked to your friends, seen some videos on YouTube, something like that. Maybe you're taking the course the second time. Do you have any questions? Anything? All right. Am I speaking too fast? Can you follow me? Is there anyone who can't follow me because I spoke too fast? Is there any part that you want me to repeat?
Hocam, it's okay, we can follow, but with mobile phone, it's not same for us as a desk, I mean.
Well, you should not use a mobile phone. I'm sorry, but mobile phone is not appropriate for this. If you're connecting from a mobile phone, there's nothing I can do. I cannot write big enough so it will be legible on a mobile phone. It just is not possible. Okay? You need a bigger screen. If I was using a mobile phone, I will be able to do anything. I'm sorry about this. It's just the hard truth. Anything else? Okay. Well, then let's move on to the phenomenon of insulators and conductors. Okay. So you probably heard of this, right? Insulator and conductor from everyday life. And we're going to somewhat idealize these concepts. Okay? So an insulator is something that insulates the flow of charge. A conductor is something that allows the flow of charge. And we're going to say that our conductors are ideal conductors. So they just let charge flow without any resistance until they come to circuits, of course. And we're going to change our mind. And the insulators are perfect. That they don't let any charge flow. So you put a charge on an insulator, it's not allowed to move. You put a charge on a conductor, it's completely free to move. Can go anywhere on the conductor. So if you push it a little bit, it's just going to accelerate in that direction. Okay? So this is somewhat isolated. Now, how does this work? Again, we use the atomic structure. So it turns out that some of the molecules and some of the atoms themselves, they form molecules, that the electrons are tightly bound. Okay? And for some of them, notably the metals, the electrons are not tightly bound. So for the metals, what we have is that we have some nuclei, and they're essentially floating in a sea of electrons. Okay? The electrons are not bound to any one of the nuclei. So when you apply some force, some electrostatic force on them, the electrons can just move. Another electron is going to take their place. Whereas with the insulators, with typically the organic compounds around you, like wood or plastics, something like that, the electrons are bound. So if you apply a force, they don't want to leave the nuclei that they're bound to. So they can't move around. They can't conduct the charge. Okay? All the charge that's being transferred typically that you see around you is by electrons. So if the electrons cannot move, the charge cannot be conducted. Right? There's the exception. You have solutions. In solutions, you have also ions that can move around. But that's just an exception, and I'll leave it to the chemists to deal with that. Okay? So these, even though there are degrees of insulation and degrees of conductivity, we are just going to assume that our insulators are perfect. If you put a charge on them, they stay there. They don't do anything. And our conductors are also perfect. And you put a charge on them, they're completely free to move. So if there's any force on them, they're going to accelerate. Okay? Now, what does this lead to? So there are some experiments you can make. And typically, a good metal, like pure copper or something like that, is a very good conductor. So our approximation that they're completely free to move is not too far off from everything, from the reality. Right. So what you can do is that you can take some charged object. Let's say the side of this is positively charged, right? And you can take a conductor. So this is an insulator. And you can take a conductor, let's say a cylindrical rod. Now, what will happen here? Okay? What will happen here is what we call induction. Okay? So what's going to happen is that because this is a conductor, the charges are free to move on it. So there are this conductor, in the beginning, it's neutral. And it is going to remain neutral in total. But what it can do is that it can separate the charges on it. So part of it can become charged one way, and another part of it can become charged the other way. Right? And this is exactly what's going to happen when we bring this. So this insulator is going to attract negative charges on this conductor to its side, and it's going to repel the positive charges to the other side. The conductor can do this. The charges are free to move. Okay? The insulator cannot, obviously. And then you're going to have something partially charged here. If I take the insulator away, these are going to attract each other. These separated charges are going to attract each other, and they're just going to cancel. I'll get a neutral conductor again. But if you keep it this way, then they're going to just remain separated. Now, what you can do is that you can charge something by induction, and the way to do that is that you ground one part of the conductor. Typically, you ground the part that's farther, but you can do the other side as well. Now, this is the symbol for ground. My drawings are horrible, I know, but there's a much better drawing, the official symbol in the book. You can take a look at that. Now, when you do this, the ground, by definition, is neutral. So it's the ground. It has to be neutral. And again, by definition, it's an infinite reservoir of charge. It can provide an infinite amount of positive or negative charge as needed. Okay? So when these positive charges are connected to the ground, they'll flow to the ground and become neutral. Okay? So this is also a conducting wire, which means that the charges can just flow freely on this wire without any resistance. And because this is neutral, this will also try to become neutral. So what's going to happen is that these charges are going to flow through the wire, and we're going to end up with something like this. Okay. Now, at this point, what you do is that you break the circuit, you remove this connection to the ground, okay? And then, so this was there when I removed this, and then you remove the conductor, the insulator that induced the charge. Okay, so a couple steps. I have a conductor that's not connected anywhere. I broke the insulator. This induced two kinds of charge on it. Then I connected one part of my conductor to the ground. This made this part neutral. Then I disconnected the ground, and then I took away the insulator. Okay. So then, because now there is no insulator inducing any force on these negative charges are just going to distribute themselves more or less evenly on this conductor. Okay, and we're going to have now a charged conductor. We started a neutral conductor, but we deposited some of its positive charge to the ground, and we end up with negatively charged conductor. Obviously, you can do the opposite of this. You can start the negatively charged insulator and induce some positive charge on this. And you can go around and play with this. You can take this, you can deposit it on something else that where it cannot escape. You can do something like a one-day graph generator. Okay. But there's a lot of room to play around. It's not very important, but this is how charging by induction works. Again, I'm guessing this is something you might have seen before in high school, but I don't know if this is something completely new. It is in the book. If you look at the book, you should be able to figure this out. But it's not very, very important. But conceptually, it is important that you understand what's going on. If you don't understand what's going on here, then you're not going to understand the more complicated stuff. Now, this is related to an instrument that you will probably see in laboratory, electroscope. Electroscope also works with induction, though there you're not necessarily charging anything. You're just separating charges.
Can I ask something?
Yes.
So on the conductor, there are only like electrons. Like there
are electrons and nuclei, but only electrons can move freely.
So the one thing that I don't understand is if there is a sea of free electrons, shouldn't all the electrons repel each other because of their negative charge? How can they just like stay in the middle without going anywhere?
They are not staying in the middle. Why do you think they stay in the middle?
Because of
what do you mean by staying in the middle?
Because of the illustration, I guess.
What illustration? Which illustration are you referring to?
The one on the board right now.
This one?
The thing on top.
This one?
Yeah.
So they're all over the place. They're not staying in the middle. They occupy. So if you have a piece of metal, that was the model for a metal, where you have sites for the nuclei, and there's an electron sea. The nuclei are just immersed in this electron sea. The electrons are not at a particular place. They are all over the metal. They're not in the middle of the metal or anything like that.
The reason why they are moving so freely is it because they always repel each other because of their negative charge?
No, the reason why they are moving freely is because it's energetically more favorable. They are not attracted to the nuclei strongly enough. So it's a balance between entropy and enthalpy. So there are a lot more states available when they are free to move. So that's the direction of entropy. And energetically, they will be bound to the nuclei, but that's the direction of enthalpy, but it's not strong enough. So if the attraction was more strong, like in a oxygen molecule, for example, then they will be bound. They will be moving freely around. Like if you take a piece of oxygen, you can make it a solid as well. There are no free electrons there because the electrons are bound to the nuclei because the nuclei are attracting them very much. So the entropy doesn't win. Here entropy wins because the enthalpy is very weak. The attraction is so weak that it's not enough to overcome the tendency of entropy. It's just how this behaves. There isn't anything magical here. Did I confuse you more?
I think it's okay. Thank you.
Yeah. Right. You're chemical engineers, or you're going to become chemical engineers. So it's never too early for you to hear about entropy and enthalpy. It's going to be your life, basically. But this is the explanation. There isn't a simplified explanation. It's just the electrons are not bound strongly enough, so they move freely. It sounds silly, but that's the way it is. They're not so free. They can't leave the metal, right? If they leave the metal, then the metal becomes positively charged, and they immediately come back. For them to leave the metal, you have to hit them, like with light, for example, with ultraviolet light. If you shine ultraviolet light on metal, then it starts emitting electrons. But like normal metals, with the normal light, optical light incident on them, they don't lose electrons. They are bound a little bit, but they're not bound to a particular nucleus. It's much more favorable for them to move around than to be bound to a single nucleus. And that's just entropy versus enthalpy. Yeah. Yes, I was going to talk about the electroscope. So this is something you might actually see in laboratory. So I'm just going to draw a model. So there is a conducting sphere here, and the conducting rod, and two pieces of conducting sheets here. So there are these are free to open or close. So they can just close or they can open. They are just think of this as two plates. The pivot point right over here. Now you can see if something is charged by bringing it close to an electroscope. Now when you bring this close, because this whole thing is a conductor, it's going to attract the negative charges over here. So this sphere is going to be negatively charged. And in response, because charge is conserved, these parts are going to be both positively charged. And because they are both positively charged, they repel each other and they just, the leaves open. So this is how the electroscope works. Now you can, of course, do this and then discharge this. You can ground this. And then take this away. And then the whole thing is going to be positively charged and the electroscope is never going to close down. So before, and sometimes this does happen by accident because this part is exposed to air. It can actually discharge through the ions in the air. And before using the electroscope, you should actually ground the electroscope and make sure that the leaves are starting closed. Okay? But once you charge it in a particular way, let's say that you charge this in a positive way, you have an electroscope that's positive all over. Let's just move this. Now you can check whether the object that you're bringing is going to be positive or negatively charged, because now you have this and you know that there's some excess positive charge over here. So what happens if I bring a positively charged object? Now this is going to bring some negative charge over here. So let me just use a second color. And it's going to induce further positive charge over here. Okay. Now if you do this, because I increase the charge over here, the repulsion is going to increase. It's going to open even more. Now, what does happen if I do the opposite? What does happen if I bring something that's negatively charged? Okay. Then I'm not going to have negative charge induced there, but instead positive charge induced. Oh, wait. Oh, yeah. And in return, I'm going to have negative charge induced here. Okay. And these negative charges are going to partially cancel, or maybe completely cancel. It depends on how charged this object is. But if it's very, very strongly charged, then you don't bring it too close. You don't induce the level of charge over here. As you bring this, the leaves are going to close. So you can figure out whether the object that you brought was similarly charged to the initial object, that you used for charge by induction, or it's oppositely charged. And this is one of the experiments that you can make to convince yourselves that there are only two kinds of charge. Okay? So no matter how,
in this example, did you bring the two of the objects at the same time?
no, I took this away, of course.
But how can at the end of the electroscope is there any positive
Which end are you
charges?
referring to? The bottom end or the top?
Bottom.
Okay.
There is positive charges right
There
there.
were positive charges, but when I brought this, some of those positive charges are going to move up here. And that's going to leave behind some negative charge or some decrease in the positive charge. It's the same thing.
Oh, okay. Thank you.
Sure. Anything else? Okay, so these interactions are also kind of working. By all means, interrupt me. I'm happy to be interrupted. But so this is the so-called electroscope. You can make obviously accurate versions of this. You can like put some scales on the leaves. You can put some distance scale over here, and you can make some quantitative adjustments. But electroscope is a simple instrument. It's not designed to make quantitative measurements really. But it can tell you whether two objects are similarly charged or oppositely charged. Okay. Now, to make things quantitative, we want to make things quantitative, we have to simplify. Now, to simplify things, we are going to introduce the concept of point charge. So this is exactly what it sounds like. It's some object that's like a point mass, which I hope you're familiar from the first semester physics, and there's some charge. Okay? So the example that you could have in mind is an electron. An electron is something very, very small. You can think of this as a sphere with a radius of 10 to minus 15 centimeters, which is really very, very small. But you don't have to. Okay? You don't have to think of an electron, especially since we are going to have point charges that are also positive. And yeah, you can think of a proton in that case. A proton is a bit bigger. It's up to you. But you don't need to have something in the back of your mind for this to work. A point charge is a concept. Okay? And it doesn't have any dimensions, it doesn't have any space extent, but it has some charge. And we can write down the force between 2 point charges. Let's say Q1 and Q2 that are separated by some distance R. And these are going to exert some force on each other. Okay? And that force is given by Coulomb's law. Force is K Q1 Q2 divided by R squared. And we're also going to write this as 1 over 4 pi epsilon naught Q1 Q2 by R squared. And so
May I
this
ask
is
something?
Go ahead.
Can we think point charge as a mass center?
I wouldn't do that. You can use anything, but I don't think it's going to be helpful. If by mass center you mean center of mass, then the answer is no. Center of mass is something completely different. Okay? And there's no center of charge. You can define a center of charge, but we're not going to go into that much detail in this course. Center of mass is not a good analogy for a point charge. Okay? So we are going to see that just like Newton's law for gravitation, that if you have a spherical distribution of mass, it acts like a point mass at its center, the outside of the sphere. If you have a spherical distribution of charge, it acts like a point charge at the center to the outside. But that's pretty much all the analogy is. The rest of so this is called the monopole approximation. The rest you are not going to use. Okay? So I wouldn't do that. But if you find helpful, go ahead. I don't mind. Whatever you find helpful, everybody thinks different. Okay? Whatever helps you, feel free to use it. If you're in doubt, ask like this. And if it's very far off the base, or if it's going to be harmful in some way, I'll try to let you know. Now, so a couple things about units. So this force is, of course, in newtons. This R we measure in meters. This charge we measure in coulombs. And the symbol for coulomb is C. So this K is going to have the appropriate units in MKS system. So in this case, it's going to be what? Newton meter square per coulomb square. And epsilon naught, the so-called permittivity of vacuum, is going to have the opposite one. So it's going to be coulomb square per Newton meter square. Okay? But so I'm going to be using this one more often than this one, but it doesn't really matter which one you use. It's again something like a personal preference. I like Gauss's law. In Gauss's law, this looks more fundamental. If you like Coulomb's law, this looks more fundamental. Doesn't really matter. But these are the units. Now, for our everyday life, typically, the Newton is a reasonable amount of force, right? You can apply 1 Newton, and it's not going to break a lot of things. 1 meter is a reasonable amount of distance, right? You just move around. Your 1 step is about 1 Newton. Yeah. So that's 1 meter. So like this whiteboard is about 2 meters wide. Now, what about 1 coulomb? Is 1 coulomb a reasonable amount of charge? Yes and no. It depends on what you're looking at. So, like the typical amount of charge that you're going to interact with, is that an order of coulomb? Typically, no. You usually deal with like microcoulombs or millicoulombs, something like that. Like when we come to capacitors and we charge them, we're going to see that they have like capacitances of microfarad and things like that. And we apply typically a few volts, and they're going to get charged to microcoulombs. Yeah? But at the same time, it's not something very unreasonable. For example, charge, another property of charge is quantized. So it turns out in the universe, there is a smallest amount of charge that you can come up with, and that's the charge of an electron. Okay? So sometimes this is denoted by Q sub E, sometimes it's denoted by E, and this is, well, let me look this up. I think it's 1.6, yeah. 1.602 times 10 to the minus 19 coulombs. And so as you see, this is something very, very small. But then you don't really deal with a single electron, do you? Right? You typically deal with an Avogadro number of electrons. Like in your system, there's an Avogadro number of atoms, and some of these, usually a small fraction, but even 1,000 of these, if they're involved, is going to have you're going to have typically a very large number of electrons. So if you multiply this by Avogadro's number, you get a large number, and if you allow for a small fraction, you get something around unity. So a coulomb is not something very totally logical, but typically you're not going to be dealing with a coulomb of charge, but like millicoulombs and microcoulombs. And if you don't remember what these mean, like millicoulomb, microcoulomb, nanocoulomb, you should brush up. Yeah? Because you're going to see these, and their meaning is not necessarily given in an exam. Yeah? It's not very hard. Like 10 to minus 3, 10 to minus 6, 10 to minus 9. None of it is particularly easy to remember. All right, so this is the magnitude of the force, and there's also a force, as you know, is a vector quantity. It's going to also have a direction, right? And we already said that the unlike charges are going to attract each other, and like charges are going to repel each other. And it turns out that this force is always along the line that's connecting these two charges. Okay? So if these are two unlike charges, then there's going to be an attractive force that's going to look like this. Okay. Now let me tell you a little bit about the notation. So F(1) means force on 2 by 1. Now some books use the opposite notation. Some books just flip these around and say that F12 means the force onto y1. Our book doesn't use this notation. This is by far the more common one. Okay? There are some notable exceptions, like I'm teaching another course this semester, and that it uses the opposite notation, but I told my students I'm not going to use that. Right? So this is what you've been using for the first semester physics. This is what we'll keep using. So this is for an attractive force. And for the repulsive force, you would have something the opposite. And all the things that you know about the force applies to the so-called electrostatic force. This is called electrostatic force. And everything that you know about the forces are going to apply to this. So one of them is that the force is a vector. Okay? So when you're adding the forces on a particle, you need to make a vector addition. Okay? So this force will lead to some torque, and then you need to use the formulas that you use for calculating the torque, but the vector formulas, not the scalar formulas. Okay? So there is a superposition, there is the vector nature, and that's pretty much it. Apart from this, this is not that much different from the tension force on a string that's just pulling some object, or when you're pushing an object, the force on an object. It's pretty much the same, but its magnitude is given by this, and its direction is given by the nature of these two. Now we can write this as a vector equation, which I'm going to do in a second. But I'd like to point out that this is very, very similar to the gravitational force. So did you actually get a chance to learn about gravitational force the first semester? I wasn't teaching this course the first semester. I don't know if it's been covered.
Yes, we have.
Now, this is the so-called inverse square force. Okay? It's extremely common in nature. Well, it's just the most common force has this nature, so of course it's extremely common, but it has some nice properties, like the Newton's theorem for a spherical distribution of charge. And this allows us to develop Gauss's law. This inverse square nature allows us to develop Gauss's law that we're going to see in a few weeks, I guess. Now, how would you write this? How would you write this force using just vectors? Okay. Now, let's be careful about this. So I'm going to erase this as well. And I want to be able to, let's say that this is Q1, this is Q2. I want to be able to come up with a vector that's along this line segment that's connecting these two charges. So what I'm going to do is I'm going to choose some coordinate system, and I'm going to say, okay, this is in that coordinate system. The position of the charge 1 is R1, the vector, and the position of the second charge is R2. Okay? And now, if I take their difference, if I take R1 minus R2, it's going to be a vector that looks like this. Right? Wrong. Is this R2 minus R1 or R1 minus R2? This is R2 minus R1. Right, R2 minus S. Okay. And I'm going to call this one R21, just as a shorthand. Okay? So let's write this here. R21 stands for R2 minus R1, and likewise, R12 is going to stand for R1 minus R2. Obviously, these are opposite each other. Okay? I'm just flipping the terms in the subtraction over here, so this must be negative that one. Okay. Now, I will also go ahead and define the so-called unit vector. And so this is R21 vector. I want to define R21 hat. And R21 hat is going to be R21, the vector, divided by its magnitude. Okay. What does this mean? It means that the magnitude of this whole vector, so this is a vector, I'm dividing it by a scalar, I get a vector. And the nice property of this vector is that its magnitude is 1, its length is 1, it's a unit vector. So I can use it just to indicate directions. I multiply this by a scalar, I'm going to get a vector that's as big as that scalar and in the direction of this vector, of this unit vector. Okay? So this is called a unit vector. And this is the common notation for unit vectors. For the ordinary vectors that can have any length, you use this arrow on top of them. For the unit vectors that has the length of unity, you have this hat on top of them. Right, now how would I use this to write my force? Well, I kind of already said it. If I multiply this by a scalar, the result is going to be a vector of the magnitude of the scalar itself and the direction given by this. Well, this is the direction that I want, and the force I'm looking for now, this kind of magically takes into account that for the opposite charges, I'm going to have attractive force, and for the negative charges, I'm going to have for the like charges, I'm going to have repulsive force. Now, how does this work? Well, for the like charges, this product is always going to be positive. Either I'm multiplying by positive and I get positive, or negative by negative and I get positive. For unlike charges, this is going to be a negative, right? So it's going to cancel this negatives. Now, what does this look like? So R12. So remember, this is the force on one due to the second one. So R12 is going to look like this. So if this is positive, okay. So this is the force on 1 by 2. If they have the same sign, then I want it to be this way. So I don't have a negative sign there. Correct. So this is the force on 1 because of 2. If they are both positive, then this is going to be in direction of R12. Any objections? If they are both positive, it's going to be repulsive. It's going to be in this direction. So this must be correct. If one of them is negative, one of them is positive, then this is going to be negative. And when I'm multiplying by a negative scalar, this one, I'm going to get a vector in this direction. And that's going to be an attractive force. What's the magnitude of F12? Well, this is a unit vector. So it's just this scalar that's multiplying the unit vector. So this is the correct magnitude indeed, right? Because this is the distance between them. And so I'm just squaring the magnitude of that vector. So this is the correct magnitude of the force, and this provides the correct direction of the force. Any objections? Did I screw something up? You might be thinking, well, this guy's 50 years old. He has done this 500 times. He probably did not screw it up, but I do. Okay. I'm a physicist, yes. Yes, I did do this 500 times. In fact, I study gravity, so I do something very, very similar. I probably did this 5,000 times, but still, I might make mistakes. You should follow carefully if I'm making mistakes. I don't do mistakes deliberately, okay? Unless I correct myself immediately, to wake you up or something. But in this case, I'm not making a mistake if I'm making a mistake. questions? Okay, so let's take go ahead.
So if the formula was R21, then it should be negative, right?
Right. So if you put R21 here, you should put a negative sign there, because R12 is negative R21. Anything else? And likewise, if this was F21, this will be negative, because if they're attracting each other, the force on 1 is going to be in this direction, the force on 2 is going to be the opposite direction. They in fact attract each other or repel each other, action and reaction. Okay? If one is applying a force in one direction on one object, the other object has to be applying a force in the opposite direction. Okay? Action and reaction does not always work in electromagnetism. We are going to see that the magnetic force is not always equal and opposite between two moving charges, but for electrostatics, action and reaction does work. So total force on the objects is going to be 0. All right, so let's take a 10-minute break, and then we're going to resume at 4 past the hour.